Welcome back, my statics friends. One of the most useful forms of vectors is finding moments or rotational effects. Now, in previous videos, we have talked about the general formula using the cross product, and in this video, I'm going to show you some more details about what that vector cross product will get you and how you can use it and some of the limitations on what it's going to try to do. So without further ado, let's get started. So in our previous discussions, we had set up our moment vector equation M as being the cross product of a position vector R into a force vector F. And so what I've got here is kind of an arbitrary shape. Now, the thing that's cool about this method, where when we were doing scalars, as we talked about in the last video, we were bounded by having to be able to do things with perpendicular distances. Okay, I had a force, and I had to find the perpendicular distance between that point and the force in order to be able to compute the magnitude of a moment. And then we would assign the direction of the vector, by hand. In this method that I'm getting ready to show, we can actually alleviate a lot of those restrictions. And so what I have here is I have kind of a general object. Now, this could be a two-dimensional object, this could be a three-dimensional object, it doesn't matter. So let's say that we wanted to find the moment at a point B, okay, and my force was acting at some other point F. Now again, A could be given as XA, YA, and ZA as the coordinates, and then B likewise could be XB, YB, ZB as the coordinates for B. So if we have those points in space, and typically you can find those, or them offhand, so this is always a good thing. To compute then the moment at B, I could take a vector from B to A, and then apply my force vector at A. Now remember, in earlier videos, we've talked about this force being a sliding vector that it can move anywhere along its line of action. So if I kind of lay the line of action in here, okay, then this is one way to compute the moment. Okay, and the thing that's nice about this, as we've talked about previously, is that this R vector does not have to be perpendicular to the force. Okay, that cross product operator that occurs in here, okay, will take care of the orthogonality. Okay, that we will maintain our perpendicularness, and at the same time, I will get all of the moments about all of the Cartesian axes, the I, J, and K unit vector axes, all in one shot. So whereas last time in our last video we had to make sure we got the right forces lined up with the right dimensions, and then we had to put a positive or negative sign on it based on its angle of or not angle of rotation, but based on its rotation about a given axis. It was a challenge, and you had to be very, very careful, and it was really easy to make a mistake. The beauty of the vectors is that it will handle all of that for you. Okay, so that's kind of how we start to set this up. Now, in reality, this is just one case. If I take a look at the same situation, okay, let's say that this is my point B, and this was my point A, and my force, is somewhere along this line like we had before. It turns out that I can compute the moment at B not by just going from B to A. I could go to any point on the line. So say I have, I called my original point A as A1, okay, but and I could use this as RA or RBA1, from B to A1, find that position vector. I'd have to know these coordinates, which you have to know those anyway, so it's not a big deal. And then A2, I could would be another point on that line, okay, that I could find the same moment about B by taking a position vector from here up to here, and I will get the exact same value of the moment at B. Okay, and likewise, another point at A3, I could take it from here to here, and that's, kind of a demonstration of this concept that we talked about a sliding vector, that, instead of acting solely at A like we had here, I could slide this vector to any point on the object, and choose a point, so maybe it's, a support location, or maybe it's, some other convenient value that you would know, that I could slide this force to here and use this R, or I could slide it to here and use this R, or I could slide it to here and use this R. It doesn't matter. It will all get me the same moment. Okay, so what does that look like with our vector equations? Okay, so if I wrote this out, then what this means is that the moment at B would be RBA1 times the force at A1. Okay, and then the moment at B could also be RBA2 times the force at A, or not times, cross product into the force at A2. And then MB is RBA2 as a vector cross into the force at, force at A, that should be a 3. Force RBA3 cross into a force at A3. Okay, it doesn't matter because these are all the same force. I'm able to slide them. They're all on the same line on those, okay? And so when they're a sliding vector, that basically means that the force at all three of those locations is the same effect, okay? And so this is how we can kind of start to use this. And so now we still have to do the cross product operator. We still have to find the position vector, but we've showed you how to do that. It's just the difference in the coordinates from the start to the end. Now, one thing that I'll point out as we kind of look at this, if you look at the labeling that I'm using on this is a little bit different than what you might see in the Beer and Johnson textbook, but I do it for a reason, is that if I'm writing this vector equation, you'll notice that the R is from B to A3, okay? Well, the moment at B is what I'm after, that those two have to match. And then the A3 corresponds to where the force is acting, that you can use that to kind of dictate which ones that you need. Now, often I know where I want to take the moment and I know where my force is applied. It's this guy, this R that I'm having, that I may, sometimes get confused and not compute the right one. But if you can use this nomenclature, watching the order of these tells you which way to draw the arrow on this picture. Remember, the first one is where you start at, and the second one is where you end, or where the head of the vector is. Okay, and so that can kind of be a little bit of bookkeeping that will tell you which R that you need and then be able to assign it that way. So use that for, some help in the process. All right, so let's keep going. Okay, so we've got this idea of a force vector being a sliding vector. Okay, and again, here's my moment equation, R cross F. Okay, but what about moment vectors? Well, because moments are rotations, it turns out that a moment is a different type of vector. In fact, the rotational effect on this object, is the same regardless of the point that I choose to do it at. So in here I've got the moment acting at A, here's the moment at B, and here's the moment at C. Regardless of where I choose to set it up, the rotational behavior of that guy is exactly the same, okay? And so for that reason, this is what we know as a free vector, and that's what gives this moment equation so much power, is that regardless of the point that I choose, I will always get the same value of the net moment on the object. Okay, now there are going to be some limitations and rules when we get to drawing free body diagrams that we have to follow, but that's a pretty cool concept and something to kind of follow in the back of our mind. So we call that as a free vector. Okay, all right. Now, one last little bit to kind of talk about in here is, what do we do about vectors in three-dimensional space? Now, for me personally, they're kind of hard to visualize. Let me get this down here, tilt the camera a little bit. Okay, and so the way that the moment vectors are outlined is something kind of like this. This is what we started with drawing the circular arrows on this, okay? And so we have a moment that's wrapping around an axis, whether it's the x-axis or the y-axis or some three-dimensional non-Cartesian axis, okay? We know that the moment vector can be expressed as the magnitude of the moment vector dotted into a UM, which is a unit vector telling the direction of the moment. Well, on this, okay, the UM is actually the unit vector that defines the axis of rotation and points towards the end that the moment is working on. So if we remember our right-hand rule here, right, I turn it this way, my thumb is kind of pointing down toward the end. Okay, and so that's why this unit vector is pointing down toward the bottom, because of the way this angle is wrapped. If this moment were going in the opposite direction, I would flip that. Okay, but this then becomes, a unit vector, and just like we did with forces on lines, we could use position vectors to get the unit vector for this particular line. So maybe I know a point here, and I know a point here, and I know that this moment is wrapping around, and maybe it's the ends of a shaft or something, that I can compute that unit vector using all the same methods that we learned back in that our force vector discussion, or forces directly along a line. It's the exact same process because it's just a basic vector is all that it is. Now, like I say, for three-dimensional objects, it's hard for me to wrap my head around, especially if I'm trying to figure out components, which way things are working. Okay, and I'm going to introduce kind of a concept known as the double arrow notation on this. Okay, so we know that, as we talked about, this is a a rotational effect with, positive moment pointing down toward the bottom, instead of writing it with these circular arrows, what I'm going to do is I'm going to write it as a double-headed arrow, just like you would a force vector. But I'm going to put two heads on it so that I know that I can't add moments to forces. Okay, but it's still a vector by its very definition. And you'll notice that the direction of that double-headed arrow is in the same direction as the unit vector that we had up here. Okay, now the thing that lets me do that I can't visualize on here is if I draw it this way and say this angle theta of the orientation of that line, well, I can go in and say, well, this is a resultant moment, apply it at the point that I'm interested in, and now I can go and find the components of this resultant by doing all the same games that you did with forces. Okay, and so now I can start to visualize, which way is this thing rotating based off of this? Well, it's rotating about a negative x-axis, and it's rotating about a negative y-axis, and now it's a lot easier for me to be able to visualize what's going on with those particular vectors. Okay, now again, unit vector for the moment, the actual moment resultant is still along that line, but mx, his unit vector is in the x direction. Well, if I looked at this guy as down and to the left, well then x has to be to the left, okay, and y has to be down in order to be able to produce that resultant. Well, that tells me that the unit vector for the moment about the x-axis then has to be acting in the same direction as this guy. So he's acting to the left, just like the one for the y direction is acting down. And so very quickly I know that that's a negative I, and I know that that's a negative j. Very, very easy to be able to start to visualize and split this thing up. Whereas I couldn't do any of this without if all I had was this picture. So that's one of the adjustments that you'll make. And I always joke in my classes that you can always tell an engineering student is taking a static exam because they're playing with the right hand, trying to get that thumb lined up to be able to see what this is doing, because this is so much more convenient. And I don't think the Beer and Johnson textbook talks about a method like this, but it works and it's very, very convenient. So I'll leave that for what it's worth. All right, so let's kind of show you the process, and I kind of put it in words, but let's show you the equations that it takes to be able to make all that happen. All right, so here's our basic vector relation between a vector, his magnitude, and his unit vector. That's the one I just showed you with the m's. Okay, it's true for the moment, so as we wrote, the moment vector is the moment's magnitude dotted into something that tells me about the okay? Okay, and the challenge is often finding this value. Okay, so now if we look at, so what can we do with this? Okay, so let's take that first moment, the moment resultant, and we know, even though I don't know their values, we can kind of start to set this thing up that the magnitude of of the vector dotted into some unit vector that tells me its direction. Okay, and we know that the resultant from that first picture, we come back up here and look at this guy and kind of overlay this so you can see both at the same time. Slide this over. Looks something kind of like this, that the resultant of these two guys is the vector sum of mx plus my. Now again, I'm not worried about the negatives on this because the unit vectors will capture that. But the vector themselves, the resultant of this guy, is the sum of those two. So we're kind of working it backwards. Where here I split it into these two guys. Now I'm going the other direction. That if I can define the moment about the x-axis plus the moment about the y-axis, the vector sum of those is that mr guy that we had happening here. Okay, so that's kind of cool. And then for each of these vectors, I can go play the game again. That the moment about the x-axis is the magnitude of the mx plus the unit vector that tells me the mx. Okay. And then the my is the magnitude of my dotted into a unit vector that tells me the my. Okay, and so for our example in this particular page, as we talked about, if I slide this down, this mx is a negative I. So if I write this, again, I've dropped the absolute value here, but it's still, this is the magnitude of the moment about the x-axis, a positive value, dotted into a negative I. Okay, and that's exactly what we saw here. Just like the my is the magnitude of the moment about the y-axis, again, a positive value dotted into a negative j, because that's the direction of the unit vector. And so that's what we have on that. Now we can just do a little bit of math and we can solve for some interesting things. All right, so if we go through and we do this, then the moment resultant is, in this case, now notice I do have just an x and a y. If this had a k component, then we could say, oh, mz as a vector is going to be, mz magnitude dotted into a unit vector and moment about mz. Okay, we can kind of set that up that way. Now, in our particular problem, because this is 2D, this guy is actually a 0k here. Okay, so, but if I write the vector in all, with all three dimensions in it, then I can write it as minus mx I vector minus my j vector plus 0 k vector. Okay, and that's a valid vector. And once I have this, now I can go play all the games that we had before, that MR in this case is mx squared, negative, because again, we're squaring the magnitude and the sign on this, and then plus a negative my quantity squared, negative my here, okay, plus 0 squared gets me to the magnitude of that moment resultant. All right, and then once I have this guy and I have this one, now I can deduce what that axis of rotation is, okay, on this as a unit vector for mr, okay, is the vector mr over the magnitude of mr, that they can easily be found on this particular problem. It's pretty cool. Okay, now something interesting that kind of comes out of all this, what we're looking at is moments associated with I, J, and K. In aeronautics, even though it's not necessarily a statics problem, the way that we control, say an airplane, this is an awesome picture of an airplane, right? Here X is down to the left, Y is to the right, and Z is acting up, that we know that there are 3 different values that are necessary to maintain control of the plane. Okay, there is the ability of this thing to rotate about the x-axis, that's known as the roll. Okay, there's the ability to kind of control which direction it's heading, which would be a moment about the z-axis. Okay, that's called the yaw. Okay, and then the moment about the y-axis on this particular object. Now again, this is kind of the center and mass of the object. The y-axis then is what controls kind of your elevation. If you point the nose up, the plane goes up. If you point it down, the plane goes down. That's called the pitch. All right, so you'll hear these terms thrown around a little bit, roll, yaw, and pitch, but all they are is they are moment effects or rotational effects on this. Now, for the plane that we have here, we could then, if I know the moment values that are being produced by, the combination of the flaps or the engines or the thrust or whatever is happening on the plane, as well as that the resultant moment of this whole thing is the moment roll vector plus the yaw vector plus the pitch vector plus a bunch of other stuff, things like the drag on the wings, the thrust from the engine at what angle and where is that being located at. I could say, well, the thrust is acting there and it's some sort of flame that way that's giving me a force that way, that all of a sudden I have the ability to be able to figure out what that's doing and how we can control the plane all off of just a bunch of statics vectors. Now again, this is a dynamic object. There's other things that happen, but just kind of in a general sense, you can kind of start to see how all of these moments and all these pieces can start to kind of play together for what's happening there. It's kind of cool, I think. So anyway, I thought I would give you that as well to kind of show you an application in other worlds of engineering. All right, so with that being said, let's give it an example a try. Okay, and so if we look at, there's my example, here we go. A fairly simple one, but just kind of showing you the math. So let's say that I want to find the moment about a point O, and my force is at A, okay, and I'm going to define the force vector as 10I minus 15J plus 20K. Now, you could create this using all the rules that we've gone over in the previous videos, however you want to create those. If you can get this guy into a vector form, which you have to do this method, then so be it. So I'm going to give you that as the vector straight away. Here's the units newtons. Okay, and we're going to say that, A is at 0, 0, 0, or sorry, the origin is at 0, 0, 0, and A is at, just say, positive 2, positive 4, positive 6 m, so it's out in 3-dimensional space. Okay, and we want to find then the moment that this force makes about that point O. Okay, well, the way that we set it up, we draw kind of our sketch of the vectors that we need. Okay, so like we said before, MO and FA means that my R needs to be from O to A. Remember, these two guys match. Okay, so the O's match and the A's match. So a vector from O to A is the vector that goes from here all the way up to here. That's my O to A. Okay, and this is my point of interest, or the point that I'm choosing to compute the moment at. All right, so now if we remember, this had coordinates XA, Y, A, Z, A, and this has XO, Y, O, Z, O, that I can find that position vector by taking the differences in the X, Y, and Z values for A minus O. So that's what I've done. I've done 2 minus 0, and 4 minus 0, and 6 minus 0, all for I, J, and K, gets me a position vector of 2I, 4J, 6K. Now, if your point was not at 0, 0, it was at some other value, that's fine. Just plug those in to the O's and you'll be in good shape, okay? It will self-correct itself on this, and it will change your moment value because your R changes, okay? But at the end of the day, it's still the same net sum. All right, so there's my R, and we've got our F. Now we're ready to do the actual cross product calculation. All right, and so again, here's my moment. I'm restating here, and this will be in the notes when you guys get them, that, that our subscripts have to match. That's what we want to make sure of. It's a 3x3 determinant. This is our cross product operation. First row gets I, J, and K unit vectors. The second row gets the R, and the bottom row gets the F. Okay, so this is Rx, which was 2, and Ry, which is 4, and Rz, which is 6. So all of these guys are coming down and populating that first row. Okay, and then my force is just going to be the values that we saw up here for my force vector, 10, minus 15, positive 20. All right, so if I do that, then here's my 10, minus 15, positive 20. Okay, and so if we look at that, we can run through our math, just doing our determinant. Again, I'm going to leave this kind of as an exercise. I did the math very quickly, but it's I times the determinant of 4, 6, minus 15, 20. So that's 4 times 20 minus 6 times minus 15, okay, which will get me a 120i, 80 minus, no, it's 170i. My apologies, which means I've got a math error. 1 second. All right, sorry about that. Had to correct a quick math error. Okay, so going through and calculating all of this, then we have 170i plus 20j. Now again, in our formula, we were doing the I, we did that one already. We went into j, it's a minus a j vector multiplied by the determinant of 2 and 6 and 10 and 20. So 2 times 20 minus 6 times 10 gets me this guy. So that's going to be a positive 20, because that's 40 minus 60. And then it's a minus gives you a positive. And then k is then 2 it'd be the determinant of 2 and 4 and 10 and minus 15. So 2 times minus 15, okay, minus 4 times 10, okay, which will get me then to a minus, should be minus 70 for the k value. Okay, and then I'm with that, now I've got the components. I can find the magnitudes, summing the squares and square rooting. That gets me 184.9. And then from that, I can now tell you what the axis of rotation of this particular object is by finding the unit vector that we have. And that's the mr over the m. And that's going to be 170 divided by 184.9 plus 20 over 184.9j minus 70 over 184.9 times k. And so your unit vector on this is 0.919i plus 0.108j. And minus 0.379. And I apologize, there's still a bit of an artifact on that. So it looks something kind of like that. All right, so now if you wanted to test this to verify, and this is always a good idea, I didn't do it in this example, but you could check. The one thing you want to make sure of is that these coefficients, if I square their coefficients and then sum them and take the square root, this should come out to be about 1.0. Now it won't be exactly 1, just because of the round off errors that are happening in this. But it should be something like, 0.999 or 1.001 or something. It should be very, very close to 1 to indicate that this is indeed a true unit vector coming out of our calculation. So now, what can we tell from all of this is that we've taken this, again, it's a 3-dimensional force, at a point in 3-dimensional space, and found the moment about some other arbitrary point, and we came up with this resultant vector that we have here. Well, it turns out that this guy is the mx vector, this is the my vector, and this is the mz vector. And so you can very quickly get a sense of what these moments are doing relative to those Cartesian coordinate axes that we set up. So it's kind of a cool feature, because again, at the end of the day, this is a resultant. Well, it's the sum, the vector sum of these 3 pieces, right? And that's all we've done, is played that game and been able to kind of continue on manipulating and learning about what it is that this information can tell. Because again, moments are complex. I know this 3-dimensional guy, I have no idea what it's doing. I can kind of get a sense of which way it's going, but there's no way that you could tell me the axis of rotation without doing this vector calculation. Okay, and so I wanted to kind of at least illustrate that part of the step. It's a very, very powerful concept, but you'll notice other than this calculation, the cross product calculation up here, the rules are nothing different to what we were doing with forces. Everything else is the same. Okay, once you start here with the resultant force, I can find magnitudes, I can find unit vectors, and you're off to the races, so to say. Anyway, I apologize for the math error on that. Got it fixed, so that's a good thing. As always, leave us some comments down below. Let us know if it's making sense to you or if you've still got questions. And be sure to like and subscribe to the channel, and we will see you guys in the next video here shortly. Have a wonderful evening. Happy engineering. Bye.